Pamela,
Hello.
so how are you feeling?
I am going to likely cough and have to mute during this hangout. I am still fighting the last dregs of the strep throat that tried to eat my entire ear, nose, throat, lungs, everything.
Yeah, and I think it's kind of interesting now as we look back. Last time we talked, you were all like, oh, I've had some bad sushi and I think I'm going to need to push this back. And then the bad sushi is lasting an extra day and now my throat hurts.
Yeah, it was wishful thinking. I was in denial. I didn't want to I was supposed to be on vacation last week.
Yeah,
Instead, I spent the entire week sick as a dog, doing my imitation of a 5-year-old who has an earache and
yeah. Did you work?
sad. I did what I had to do to prevent the world from collapsing around me.
Then it was a vacation. I know, it's just not fair. So for those of you who have no idea what it is that you stumbled into, this is going to be a recording of an episode of Astronomy Cast, episode 377, Thompson finds the electron. Yeah, so we'll take like half an hour to record our episode, and then I don't know if Pamela's going to have any energy to answer any questions, or because literally we are going to be using up all of your stored energy for this one recording. So you let me know how you're feeling, and we'll sort of stick around after.
We'll wing it as we go.
Yeah, that sounds good.
I think it's more a matter of, based on how much I'm coughing, we'll decide.
Yeah, okay. Yeah, we'll listen for the coughing. So this is a live interactive experience. You can watch the show, but you can also talk to us and ask any questions that you might have. So I'm going to say hello using the Q&A app to Tom Van Scotter, Guido Bibra, Tom Nathy, Jim Meeker, Albert Braun, Thomas Traniker, Nancy Graziano, and Nathaniel Sanchez, Pam Kingsley, Peter Waldman, and that is it. So, hey, everybody. Someone is saying that I should check my mic. Hold on, let me check my mic.
You do sound like maybe you have the wrong mic. It's a little echoey.
Weird, I know the problem. Hold on. Good one. This is why we do this.
And I am oblivious to this, so thank you guys for doing this. I should not be oblivious to Fraser's audio quality. I'm totally oblivious.
Hold on.
You're now lagging, but that's okay.
Just wait a second. Wait for it. Wait. I'm going to have to reload this browser window.
That's okay. We're both logged on as Astronomy Cast.
Or I can just do this recording. Let me try swapping. Okay, let me do one more time. Can you all hear that? Boing. Okay, I'm going to reload the window. I'll be back in 1 second.
Okay.
Sorry.
I feel like I should introduce the fish. His name is Marley. He is a very angry beta, as all betas are.
No, I do not have access to the fancy microphone for this recording.
Do you need to reboot?
I could reboot, but I will have it for the actual recording, I believe. Let me see if it's getting picked up by my audio software.
Okay, so as long as Audacity sees it, we're good.
Yeah, I see it in Audacity.
Okay.
Testing. Yeah, there it is. So you guys are going to have to trust me that I've got the good microphone for this episode. Wow, boy. Thanks, everybody. That's awesome. Okay, all right. So yeah, so we will record the show, and then we'll stick around, answer some questions. Let's get cracking. I'm about ready to press record.
I am pressing record. It is not recording in mono. My bad. I'm nothing if not consistent. Okay, recording in mono.
Also recording from the proper microphone, I promise. Okay, let's get rolling. Astronomy Cast, episode 377, Thompson finds the electron. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. Happy Victoria Day.
Happy Victoria Day to you.
You don't even know what that is, but that's fine. It's a Canadian thing. All the Canadians will be nodding sagely, and they'll go, for the first time, they'll realize that I'm not an American, but actually a Canadian.
Hey, my husband's Canadian, and now I know I need to go tell him Happy Canadian Day and feel guilty that I didn't know earlier today.
Yeah, exactly. So have we got anything to... Can people still donate for the Hangout-a-thon?
Yes, they can. I have not yet taken the page down, and so if you want to add your glorious donations to our yearly massive capital campaign, we'd greatly appreciate it. It's cosmoquest.org/hangoutathon.
Yeah, and we really appreciate your support. It was a great, very successful Hangout-a-thon this year, but we definitely need to raise a little more to kind of just smooth out the rough patches as all of those grants that Pamela's working on
are pretty much all we have to get us through until October. Because we're in an unfunded extension because sequestration.
Okay, so let's get rolling with the show. Here we go. So at the end of the 19th century, physicists were finally beginning to understand the nature of matter itself, including the discovery of electrons, tiny particles of negative charge that surround the nucleus. So here's how J.J. Thomson separated the electrons from their atoms and uncovered their nature. So let's build up into sort of figuring this out. So J.J. Thomson, sorry, Preston. Yeah, I switched microphones again. I figured it out. I got it working. So I'm back to the blue snowball. Sorry, everybody. And sorry, Preston, but he'll catch this one really quickly. Okay, so let's go back. So J.J. Thomson, who was this guy? And what led up to this series of experiments to search for the electron?
He was a professor. He was at the Cavendish Laboratory at Cambridge University, which is kind of one of those places where all the early let's do things with particle physics and what would later go on to be called physical chemistry started out. And
about what time are we talking about here?
So he got there in 1884, or he got the position in 1884. And the work that we're talking about today pretty much culminated in 1897. So we're looking at work that was done in the 1800s.
And so I guess what was the line of, what was Thomson attempting to understand? What was sort of the setup that he was doing? And what was the hunch?
Well, it wasn't so much a hunch as a, how does that work that was going on? It had been realized that if you take a tube, a cathode ray tube is what they call them, remove as much of the gases inside of it as possible, try and create a vacuum, and then add positive and negative hookups, basically cathode and anode, and send electricity through the tube, you're going to end up with this weird fluorescence where the whatever it is that's going on hits the side of the tube. And there was this debate at the time on what is the fundamental unit of matter. Is it the atom? There was a debate on, is this thing that's going on with cathode ray tubes, which were not just scientifically interesting things, but they are kind of the it demo of the time that you did to amaze audiences. No one quite knew, is this a particle phenomena? Is this a wave phenomena? What's going on? And Thomson was basically trying to get to the bottom of what's happening with these cathode ray tubes.
Yeah, I think people don't realize that back 100 years ago, scientists would go on tour and do demonstrations of scientific experiments, and they would fill audience halls of people just there to watch them perform experiments, which
the Mythbusters do today.
Yeah, but it was just people would go see the theater, or they would go see a scientist perform some experiments.
And these cathode ray tubes were one of the ones that were particularly annoying because we didn't have really good vacuum technology yet. And so depending on how much gas was left in, they glowed in different ways. And it was just frustrating. Other researchers, Hertz, for instance, had tried to see what would happen if you took a cathode ray tube and exposed it to magnets, to electromagnetic fields. And they weren't coming up with anything really definitive, which is where Thomson's like, okay, let's just step back. Let's do this completely right. And he did a very systematic experiment where he looked at how both electromagnetic field, well, how both an electric field and a magnetic field would affect the path of the cathode rays.
And did they know what the cathode rays were? I mean, they
Not a
knew that,
clue.
right? So they knew that they were hooking it up to a form of electricity, and this was generating something, which cathode rays that were coming out, and they were actually being detected on a surface on the other side.
And one thing I'd like to point out at this point that just kind of amazes me is like those old bulky TVs and monitors that a lot of us still have randomly hiding in corners of our house. Those were called CRTs because they were cathode ray tubes, just writ large and much fancier. So the technology that we're talking about in the 1890s is technology that at the time they didn't know had any practical uses whatsoever. Thomson didn't think cathode rays could really be used for anything beyond entertainment. And so when you fund basic research, you never quite know what you're going to get out of it. So his basic research is what the heck is going on with this glowing tube.
Okay.
And what he did was he took a glass tube and worked really hard to get as low a gas pressure inside the tube as possible. This way, there was less gas inside that might potentially get excited by whatever was going on. They knew whatever the phenomena was, it carried charge. Now, the problem is that an electric field can get blocked by a variety of different things. This is why cell phones don't work real well on airplanes, for instance. The gas surrounding the cathode rays inside the tube, it would get excited, it would generate its own electric field. All of this would serve to block an external electromagnetic field. So the only way for him to really see what was going on was to get rid of all of that gas. Royal pain when you're working in the 1890s, but he did it. And he ended up becoming the first person to be able to bend the cathode ray with both a magnetic field and an electric field. He was able to figure out from the magnetic field that this was something that was negatively charged based on how they understood how positive ions and negative ions reacted in magnetic fields. So he started out with well, now I know it's something that has a negative electric charge. And the question is, what the heck is it?
But how did they know that they were dealing with a particle and not like light? You know what I mean?
Well, light isn't charged. So first of all, there was the light doesn't carry charge, light doesn't have mass, whatever this is. They were able to first get at it has charge.
Right, and different amounts of charge and different amounts of.
Well, no, it always has the exact same amount of charge. That was one of the particularly annoying things, is it had a constant mass to charge ratio because all electrons have the exact same charge.
But if you crank the electricity up higher, you make it deflect more, right?
No, because each electron has the exact same amount of charge.
Okay.
It's one of those things that's completely non-intuitive. And so what mattered here is, what is the speed of the electron? Sorry, I'm going to get through the episode.
You'll do it.
So he was able to go ahead and measure the velocity of the electron by looking at the difference in how the electric field and the magnetic field were able to bend that cathode ray. And by getting at that velocity, he was able to figure out this is something that's moving at a significant fraction of the speed of light. So now we have a charged something that has velocity. We're going to call that a particle.
And I love the name, the original name that he came up with it. Do you know that?
I don't know what
He called them corpuscles.
Corpus. Yeah, no, that's true. It always makes me think
Yeah.
of blood cells, which I think is what he was thinking of as well.
Yeah, yeah.
And so he was trying to figure out, okay, so now what does this mean? So there was a whole series of systematic experiments. The first one was getting at what is the velocity of this, and it was 1/3 the speed of light, so 60,000 miles per second, 300,000 kilometers per second. Sorry, no, did the math wrong there. 1/3.
100,000 kilometers per second.
Yes, 100,000 kilometers per second.
Do you want to say them both?
Yeah.
Yeah. Okay.
So he was able to first get at the velocity, where he found it was 1/3 the velocity of light, which is 60,000 miles per second, or 100,000 kilometers per second. So these are fast-moving, small things. Now, this raises the question of how the heck do you get something going that fast? And low mass is part of that, but it took a while to get to the low mass. And what he actually got to instead was the charge to mass ratio, and then the realization that these things have about the same charge as an ionized hydrogen atom, which is a fancy word for saying proton. And it was between those two that he figured out this is something that has a mass that is 6,000 times smaller than the mass of a normal hydrogen atom.
Right, but at this point, like when Thomson was doing this work, they weren't even sure that if matter was just like atoms themselves were just little balls, just little marbles that made up a larger block of matter, and they weren't really sure if there was any particles that made up the atoms themselves.
Right. And there was the weirdness of understanding that there were these different charge amounts, different, so you could ionize something to different levels. There was starting to be the realization that you have different isotopes, so things that behave slightly differently, but are really the same atom. So there was a whole lot of confusion going on. This was really the point in time where physics and physical chemistry started to split apart. Nowadays, a lot of those problems we throw into the physical chemistry part of our way of dealing with research on these things. So with the understanding of now I have something that is 6,000 times smaller than your hydrogen atom. Now with the understanding of, this thing that I have is also the same charge in the opposite sense. So negatively charged versus positively charged, but same amount of charge as that ionized hydrogen, which is a proton. What does this mean?
Mm-hmm. What does this mean?
Well, he got it wrong.
Oh, okay.
This is one of those awesome turning points in science where they're trying to understand things. So one of the things that had him completely perplexed is with the cathode ray tubes, while they were trying to figure out what the heck was going on, one of the tests they did was to put a piece of foil inside the cathode ray tube to see if that piece of foil, they used gold foil because it's really easy to get gold foil that's only about an atom thick. They used basically atomish thick gold foil, shot the cathode rays at the foil, and as near as they could tell within the lab conditions of 1897, the cathode rays quite happily went straight through the foil, which was perplexing. And so this...
why was it perplexing? Were they expecting them to bounce off the atoms of gold, or were they expecting them to get deflected by the gold?
Well, it's basically the idea of if you have a solid object, why is a particle not going to get stopped by the solid object? So the foil was perceived as a solid. It was figured if this was still when we were debating whether photons were waves or particles. And so it was thought that waves were able to go through solids, whereas things like particles would get stopped by the solids.
Right. And it would be like shooting bullets at a brick wall and them going right through the brick wall and there being no damage to the brick wall. Right.
Exactly. And when instead they found that they had something that they could shoot at the brick wall and it would happily go through, that had velocity, mass, charge, all these other things, it made them start to rethink just how solid are atoms. And that was a completely new way of thinking. Now, while Thomson was trying to figure all of this out, what he came up with is what we now refer to as the plum pudding model of the atom. The idea here, have you ever had plum pudding? Is that a Canadian thing?
No, I just remember learning that model.
Okay, so basically the idea is you have this gelatinous mass, basically plum pudding. That's kind of cruel for the plum pudding. I do like it. I just have no clue how to explain it. You have this region that is the atom that has within it this consistent mixing of the electrons and whatever it is that is giving the atom its atom characteristics. Hadn't gotten to the neutron really, hadn't gotten to the proton as completely, still figuring these things out. It's all kind of fuzzy. So working on the idea that you have this mixture of electrons and stuff, protons, neutrons, we'd come to find out. He saw all of this as mixed together like your grandma would do in the kitchen with a bunch of ingredients. And that mixture with the electrons moving inside the mixture, it wasn't like they were baked in like actual plum pudding. With them baked in, with them orbiting inside the plum pudding, you end up with this atom.
Right. And if I understand, he thought there was like a lot, like thousands of electrons, all, because of the amount of mass required. After he detected the amount of mass, he realized that, wow, they're very light. So there needs to be a lot of them to sort of help make up the mass of this atom.
Or the protons just have to be very massive. They were fairly quick to start figuring out that the protons have this one charge to mass ratio. Therefore, they're heavy, in this case, proton being ionized hydrogen. Whereas the electrons have this really radically different charge to mass ratio, leading to really low mass. And where they started to wonder is, does this mean that the atom is mostly empty? So even though he has this plum pudding model where everything's mixed together, that mixed together still had a lot of empty space in it. And it was that empty space in the plum pudding model that allowed the cathode rays to go through the gold foil.
Right. And so sort of what happened next, because as you said, he guessed wrong. But I mean, his student, right? We talked about the Milken experiment that helped determine the charge of the electron. And, his students were people like Rutherford, Bohr, etc., right? And they went on to really get to the bottom of this. And
it was Lord Rutherford. To be fair, Thomson went on to get knighted after he got his Nobel laureate, but Rutherford kind of started there a little bit earlier. It was Lord Rutherford who, in 1899, set up experiments to start to get to the bottom of this. And so what he did was he set it up, and it took him a long time to get all the way there. His results were finally published in 1911. He set up experiments where he had the gold foil and shot the electrons at the gold foil and had around that a bunch of different detectors, photographic plates, different ways of detecting what was going on, and was able to realize that while the bulk of the electrons happily went straight through, those that didn't ended up deflecting in a completely random way that seemed to indicate that you had a dense sphere that was making up this, well, a whole series of dense spheres and empty space that was making up this gold
Right.
foil.
And so, I mean, just to use that analogy again, right? It's like you've got the brick wall and you're firing the bullets, and most of the bullets pass right through. And every now and then, one of those bullets ricochets off by 45 degrees. And this is where they realized, yeah, as you said, right, that the atom was really composed at the very center was something really dense. And then there was empty space around it that nothing was being interacted with.
And another way to look at it might be, imagine firing rubber bullets that bounce quite happily, not the normal ones, but like happy clown rubber bullets. I don't know if such a thing exists.
You just invented them.
I just invented
We'll
them.
do a Kickstarter.
Let's say that we're firing super balls. So we have a kid's toy gun. We're firing super balls at a wall made up of basketballs. And most of the time, the super balls pass between the spaces in the basketballs. But periodically, they either hit head on and come back and attack you, hit at a weird angle and bounce off. And that distribution of how they bounce off allows you to track what is the shape of the basketball. You could, for instance, replace the basketballs with some sort of weird geodesic shape that was still a bouncy substance of some sort. And you could map out the shape of those, again, based purely on...
Right. If they were cubes, you would expect a lot of them to bounce straight back, while some of them would bounce at a little bit of an angle. But in this case, you could really... And so they were able to really tell, no, it's spheres at the middle of these atoms.
Exactly.
Yeah.
And so this was one of those really neat points where you have an experiment that started as we have no clue what's going on. And I'd love to know why someone got the idea to run electricity through a glass container of mostly vacuum. This is the type of thing that started way back with Benjamin Franklin, working with various, basically, jars of electricity. People continue to play with their glass vacuum shapes, sending electricity through them in different ways. Got to the question of what's going on, the discovery of the electric field, the magnetic field. Let's see what we can do with this, with both of these. Came up with a model of the atom, ran experiments to see if it was right, realized it was completely wrong, fixed that. And systematically over time, we got a deeper and deeper fundamental understanding of how atoms work. Now, at the same time, while they're doing all of these experiments, they have to start perfecting the vacuum pump so that they can get lower and lower amounts of gas inside these gas tubes. We're getting higher and higher precision control of the electric fields and the magnetic fields. Eventually, these technologies, as we start to master electricity, would allow us to precisely pick where's that electron getting sent to, allowing us to first sweep it back and forth, then sweep it up and down and back and forth, allowing us to eventually produce
television.
Exactly.
Yeah.
And this is the story of scientists trying to figure something out, fully saying this has absolutely no purpose, being dead wrong in the no purpose, and creating something that we've all wasted great segments of our life in front of.
Right. So truly that was the runaway experimentation with cathode ray tube gave us television.
Exactly.
Yeah. Thanks, Thomson and friends. So, I mean, Thomson sort of thought it was the plum pudding, that everything was sort of evenly distributed. Other people like Rutherford and such came along afterwards and really helped come up with the other ideas, that it was that you had this hard core with the electrons around it. But what did they sort of think the electrons were doing around the central nucleus?
Well, the idea of orbits didn't take too long for them to get to. I mean, they figured they weren't just hanging out. They knew that there was some sort of an attraction going on, but they clearly weren't merging together. So this is where you start getting at the idea of something with velocity in motion around whatever. leads you to the idea of orbits, motion. The motion prevents things from colliding, collapsing together. But it would still take a little bit of time before we started to get to the idea of discrete energy levels. It would take a lot more work. Planck needed to start to join the field. We need to start to figure out what the heck is this ultraviolet catastrophe, black body radiation. But all of this, again, was happening in this brief period from the 1880s to the 19 teens that we've been focusing on for the past couple of months now, I think.
Yeah. Awesome. So I think that wraps up this week. We'll talk to you next week, Pamela.
That sounds good. And it will be my turn to be having a holiday. It'll be Memorial Day here in the United States, but
Awesome.
I'll be here to record.
As will I. All right. Thanks, Pamela.
Okay. Bye-bye. I need to refill my hot tea.
You only coughed a couple of times. I saw you muting yourself.
You'd think that throats would be designed to be able to cope with seasonal allergies and the occasional sinus infection without trying to consume your lungs.
How much more
It's a
evidence do you
definite
need for
design
evolution
flaw.
here?
It's a design flaw.
Yeah, we're made of meat. Just make sure this gets into the drop boxes. All right. Boom. I hope I can fit the Dropbox size. Cut some stuff out of the Dropbox, please.
I will do that right now.
All right, let's look at some questions. Okay. Tom Nathan says, I have a whole bunch of electrons who are just ionizing to hear this show. Good Old Beaver says, hello, everybody. May all the viruses and bugs have been sucked into a black hole where they belong.
If only.
I
think the problem is we had graduation on campus on Friday, which means I was exposed to like all the plague carriers.
Pam Kinsey says, can you do some episodes on space programs from the smaller agencies? Aside from NASA, ESA, and the Russians, you rarely mention anyone else, like JAXA, Chinese, Brazil, India. That'd be cool.
I thought we had done India and JAXA at some point.
I don't know. It's going to take a bunch of research.
And we just didn't get to it. Yeah.
Fred Miller asks, when will there be a neutrino episode? We already did one.
Probably in year 1 or 2.
Yeah, let me see.
It was a while back.
If you want to know the topic, search Google for Astronomy Cast and then The Thing. So yeah, 32. Episode 32. Do a search for Astronomy Cast Neutrino and you'll get that. Hugo Burnham asks, is there an equal number of electrons in the universe to the number of protons? No, right? I mean, protons have many more electrons, don't they? Oh, well, hold on a second. No, the other way around.
Wait, did you say neutrons or protons?
Protons and electrons.
It's a grand scheme, average, small scale, not necessarily. Because there's no intrinsic charge to the universe.
Really? So the universe is neutral?
Yes. Grand scheme. Small scale, not so much.
In other words, they pretty much match at the largest scale.
Yeah.
Wow. That's cool. I guess that's how you would say it, that the universe would be charged positively or negatively. And then people could blame all the reasons why that we live in a negative universe. But no, this universe is neutral. Josh Andrews to know, what's your favorite toy? Some toys in the background there? I don't know if you do have some toys in the background there.
Oh, I think I do. Well, I have a stuffed bear in the background. My My favorite toy right now in terms of non-scientific toy is my bicycle. My favorite toy for doing science is well, I like to play with the internet and write software to manipulate large databases that require abusing Amazon Web Services because my iMac isn't that good.
Is your iMac fairly new?
I want to say it's a 2012, but there are times when just opening Photoshop will cripple whatever SQL thing I'm doing.
I'm pretty happy using I hate to say it, a Windows machine, a desktop. Like I've tried to do this from my Mac and it just all gimps up, but just a big Windows box with a lot of RAM.
I just want my lamp stack. Give me a lamp stack and I'm good.
Okay, so we've got some questions. Oh, hold on. Let's see. So, this is a great question. Okay, so this comes from Giuseppe Repisarda. And so if you took a duplicate of the Earth and scaled it down to something that you could hold in your hand, say an average globe-sized, how heavy would it be?
I mean, if you think about it, the Earth's average density, we're basically silica. So
It would be as heavy as a rock.
it's a rock.
Yeah. Awesome. I love it. Okay.
A very dense rock.
Samuel Johan wants to know, I'd like to know why Uranus is lying on its side.
We're not entirely sure. We did actually an entire episode on Uranus where we discussed a bunch of the current models for it, which range from collisions to torque. Probably it's a collisional issue.
So some kind of interaction with another object in the solar system, another planet.
Warped.
Yeah.
Or
And does that object still exist, or is that object long gone?
It probably would have, just sort of like they call it Theia, the object that hit the Earth when the moon was formed, was a Mars-sized object that hit the smaller pre-current Earth object. The collision left the moon and the Earth. Whatever happened with Neptune, probably, clearly you don't have a large moon formed. But it's a gas giant, so it would have had a completely different kind of fate, or at least an ice giant, which still would have had a completely different kind of collisional process.
This question comes from Razor Mado. Question about pulsars. When we hear sounds coming from pulsars, is that actually its sound or a sound that scientists are giving to it?
It's a sound we're giving to it. Our ears don't hear at those frequencies.
Or we don't hear radio waves.
Well, there's that too.
Yeah, yeah. And so, like, they can be going thousands of times a second, right?
Yeah.
And so, kilohertz, right? And so we wouldn't hear those, if even it was sound waves, which it's not, but it's actually radio waves. They're converting radio waves into sound waves, and then they're slowing them down. So, no, you couldn't actually hear a pulsar.
Yeah, I'm looking to see what so the human ear hears basically from 8 kilohertz to 22 kilohertz. So these are actually at a lower frequency than what the Earth can hear. Not the Earth, the ear can hear.
I get so many adorable emails from kids, high school students and stuff. Let's see. If anyone's got a question, throw them at us. But okay, so Leo Vagoda says the most abundant isotope of hydrogen contains no neutrons, but most of the heavier elements were made up by fusing hydrogen atoms, but all those elements have neutrons in the nuclei. So where did all those extra neutrons come from?
There's a lot of different nuclear processes and decay processes that produce neutrons, and it's actually through neutron bombardment that you end up getting some of those really heavy elements where you bombard them with neutron upon neutron upon neutron, and some of the neutrons end up undergoing decay processes that lead to the neutron becoming a proton and a anti-electron, which is called a positron, and there's neutrinos involved to conserve stuff and things. So you have different processes. You're also looking at, as you go through the nuclear processes, in different of the energy release mechanisms of fusing things together, instead of just going up from one proton and one proton to two pure protons, you end up building neutrons into those processes as well, where the energy is released in the process of protons converting into neutrons. So it goes both directions.
Right. But like, fusion in the sun, you take 4 atoms of hydrogen, not a neutron to be found, squish them together, gamma radiation is produced, goes through a bunch of different reactions, and you end up with a helium atom that has neutrons, right?
It's not entirely that simple. I'm pulling up the details before I accidentally lie.
Well, that's why I said it goes through a whole bunch of reactions.
Yeah. So what you end up with is you have 2 protons coming together that form a proton and a neutron. So right off the bat, you're creating that hydrogen with a neutron in it. You then combine the proton-neutron combo, deuterium. You then combine the deuterium with that regular hydrogen atom. That gets you to your first helium atom. You then combine those helium atoms to end up with protons being given off, and that helium-4 that is the 2 protons, the 2 neutrons. And that's all part of what's called the proton-proton chain.
Yeah.
So the 2 processes that we worry about in stars like our sun is the proton-proton chain and what's called the CNO cycle.
Let's see if I got any more here. So Emily asked me, right now my science class is doing a project where we can choose how to make our planet better. And I'm wondering why we can't just send garbage to space. Why can't we send garbage to space?
It's just way too expensive. The problem is it's extraordinarily energy intensive. And when I say expensive, I'm not talking money. I'm talking the entire cost, the carbon footprint, what it does to the atmosphere with other gases as well, the probability that it's going to explode like rockets apparently like to do, as the Russians keep proving, and is going to end up, instead of, there's that idealized idea of let's take all of the garbage and send it to the sun. It's just not going to get there, and instead we're going to end up with more space junk. At the end of the day, what we really want to do is massive recycling and a better job with composting to get that carbon going back into the biomass, to reuse the metals so that we don't have to keep doing mining. Garbage isn't a bad thing. It's a byproduct that we need to find more effective ways of using.
Yeah. Would you be willing to pay $1 million to have your garbage taken away each week? That's all.
That is yeah. If you think about it, the average person produces how many pounds of garbage per week?
Oh, I don't know. But, when I think about like the weight, like maybe it's like 30, 40 pounds of garbage, just your household waste, right? When you think about what you leave on the corner every week. So I think I did the math, and it's not quite the value of gold, but a kilogram put into orbit is worth about as much as a kilogram of gold. So it's just so expensive. I actually did do the math. I did an article, must have been 10 years ago, and I actually did the math and calculated the quadrillions of dollars it would cost to launch our garbage into space.
Well, and we're also losing those resources when we do that, which is bad.
Yeah.
We only have so many resources here on the planet Earth, and shooting them off into space, we talk all the time about worrying about when we're eventually going to run out of fossil fuels, because those are a limited resource that you have to have death of past biomass. In this case, the Jurassic period dinosaurs and plants and everything else went into creating your oil, your coal, all of those things. Eventually, we're going to run out of dead dinosaurs to put into our car engines, and we can't fix that. Well, if we start shooting metal into space more than what we're already doing, it's going to have a significant impact on, well, how much metal do we have left that isn't already tied up into buildings? It's a lot of different stuff that we have to really worry about as we do this.
Okay, so I got one last question for you, and it's an easy one. This one comes from Anemone Joseph. Is the universe spinning? So we think about the planets, we think of the solar system.
Spinning or spitting?
Spinning.
Okay, that makes more sense.
Yeah. So you can imagine, right? We think about galaxies spinning. We think about solar systems spinning. Everything kind of spins. Does the universe itself spin?
No way to know.
There's no way to know. So maybe. But probably maybe not. We don't know. The part that's kind of interesting is we can tell your sort of absolute motion away from, say, the cosmic microwave background radiation, but that's as far as you can go.
And since we're probably only seeing a small percentage of the universe, I think the latest numbers are at most we're seeing 2 or 3% of the universe. It's not like we can start to measure differences due to any rotation that's going on that small of a scale. Yeah.
Wasn't Mach asked this question? I think Mach came up with this sort of mind.
I'm not sure.
Yeah, just this idea, right? That if you're an astronaut out in space and you didn't interact with anything and you were spinning, would you know?
Well, and if you think about it, you do need to start worrying about the Earth's rotation with large-scale ballistic missiles. But for the most part, you're not going to notice the Earth's rotation just in the difference between a mountain valley and a mountain peak. So even at those scales, we're not noticing these things.
Yeah. Okay, cool. Well, I think I know you need to go and drink some more lemon tea, and I'm going to go and enjoy this beautiful Victoria Day weekend. I'm going to go swim. We swam yesterday for the first time of the season. It was a little brisk.
Wow.
Yeah, but it was nice to do it. So
cool.
Well, hey, thanks, Pamela. Thanks, everyone. We really appreciate you joining us this week. And I don't know what we have planned. It's in the list. But we got I think we got one more experiment episode planned.
I think so.
Yeah, and then we're going to move on. So, well, thank you so much, Pamela.
My pleasure. I'll talk to you later, Fraser.
See you all next week.